Hi everyone. Let's try to solve this problem from quantum mechanics. And in this problem, we have been given Gaussian distribution where this rho of x is actually the probability density. If you are familiar with the sqaure notation, so it's actually this sqaure given. Now we have to determine the normalization constant a. We have to determine the expectation value of x, expectation value of x square, and then standard deviation, and we have to sketch the graph of this probability density. Now let's do one thing. Let's uh, do it very smartly. Actually, there is a sort of trick which we can use, and we can find all these three things maybe in a very less time. Let's compare it with this thing: a e power minus x minus expectation value of x whole square divided by 2 sigma square. Now if we compare our results with this thing, then we can write it like this: x minus a whole square divided by this lambda can be written as 1 over lambda. Now these two things are comparable, and we can easily find that this expectation value of x is a, then expectation value of x is equal to a. So this is this one. Now we can also see that 2 sigma square is 1 by lambda. So 2 sigma square is equal to 1 by lambda, which implies sigma square is equal to 1 over 2 lambda, which implies sigma equals 1 over root of 2 lambda. So this is the standard deviation here. Now we can use the basic definition of variance, that is variance is equal to expectation value of x square minus expectation value of x whole square. So which implies sigma square we already know, 1 over 2 lambda. So this is 1 over 2 lambda equals expectation value of x square we have to find minus expectation value of x we already calculated, which is a square. So which implies expectation value of x square is equal to 1 over 2 lambda plus a square. So all the three things have been evaluated very smartly. Now this is the first, this is the second, and this is the third one. Okay, so now let's do one thing. Let's solve it using the mathematics and using the actually Gaussian integral, which is very famous Gaussian integral, and we'll evaluate all the things very smartly. See, the first of all we have to determine the normalization constant. For that we will use the normalization condition, that is minus infinity to plus infinity rho of x, which is actually the probability density, d of x equals 1. Like you might be knowing this way: minus infinity to plus infinity psi square d of x equals 1. That is, the particle must be somewhere, that is the whole probability from minus infinity to plus infinity is 1. So what we'll do, we'll directly substitute rho of x here. So minus infinity to plus infinity rho of x is a e power minus lambda x minus a whole square d of x equals 1. Now I'll tell you the Gaussian integral. There are so many actually Gaussian integrals, but I only remember one, and I evaluate whole lot of Gaussian integrals using that integral. So it says minus infinity to plus infinity x to the power 2n e to the power minus alpha x square d of x equals 2n minus 1 double factorial divided by 2 alpha to the power n root of pi by alpha. See, where n takes values from 0, 1, 2, 3, so that this would be an even number. Otherwise, if it is an odd, then whole integral becomes odd and that vanishes. Let's say if there is to the power 1 x to the power 1, so that would be odd integral, x to the power 3, which is an odd integral, so that vanishes. But only in these cases, when we put n equals 0, n equals 1, n equals 2, so this becomes even, and this formula is actually very useful. So 2n minus 1 double factorial, you have to remember two things: that is 0 double factorial is 1, and minus 1 double factorial is also 1. Okay, let's use it here. uh, a, let's take a outside because we have to find it. Minus infinity to plus infinity e to the power minus lambda x minus a whole square d of x equals 1. Now we will put one thing. Let's put x minus a equals y. That would make our things very solvable, which implies d of x equals d of y, and that would also make our things comparable with this integral. So which implies a integral minus infinity to plus infinity e power minus lambda. In place of x minus a we put y square. In place of dx we have dy equals 1. Now if we see here, we have y to the power 0. So here n is 0 actually, because here it's actually y to the power 0. So n is 0. So that means here it would be 2 into 0 minus 1 double factorial divided by 2. In place of alpha we have lambda to the power 0 root of pi by lambda, and it's minus 1 double factorial. Minus 1 double factorial is 1, and anything power 0 is 1. So this whole thing is 1. There remains only pi by lambda. So which implies a, this whole thing is root of pi by lambda equals 1, which implies a equals root of lambda divided by pi, which is actually the normalization constant. Now let's move to the second part. Which is the expectation value of x. So the definition of expectation value of x is integral minus infinity to plus infinity x rho of x d of x. This is this quantity, and rho of x is the probability density. So let's put directly minus infinity to plus infinity x. In place of rho of x we have given a e to the power minus lambda x minus a whole square d of x. Now a is a normalization constant. We already calculated it. Let's put it outside. Root of lambda divided by pi integral minus infinity to plus infinity x e power minus lambda x minus a whole square d of x. Now again we are going to put x minus a equals y. Put x minus a equals y, and which implies d of x equals d of y. Now I forgot to tell you one thing, that here when we substitute x minus a equals y, the lower limit and upper limit won't change, because by subtracting a from minus infinity or by subtracting a from plus infinity won't change the limits. Okay, now let's try to see what will happen to this integral. So which implies expectation value of x is equals root of lambda by pi integral minus infinity to plus infinity. In place of x we have y plus a e power minus lambda y square dy. So which implies expectation value of x equals root of lambda divided by pi. Now we have two integrals, one with this thing and another with this thing. So minus infinity to plus infinity, you don't worry, everything will be solvable by using that Gaussian integral. Y e power minus lambda y square dy plus minus infinity to plus infinity a e power minus lambda y square dy. Now if we see, this is the odd integral and it would be 0. There only remains this one. So which implies expectation value of x equals root of lambda divided by pi integral minus infinity to plus infinity. Let's put a outside, e power minus lambda y square dy. Now we already know this integral, we already evaluated it here, this. So it is root of pi by lambda, which implies root expectation value of x equals root of lambda divided by pi a and root of pi by lambda. This one is from this and this one is from normalization constant. So this whole gets cancelled, and there remains only expectation value of x equals a, which is exactly the same answer we find by using the comparison method. Now let's move directly to the third part, which is expectation value of x square. So using the definition, integral minus infinity to plus infinity x square rho of x d of x equals minus infinity to plus infinity x square a e power minus lambda x minus a whole square d of x. Again, let's take a outside and write its value as lambda divided by pi, and minus infinity to plus infinity, again put x minus a equals y. So let's put again here x minus a equals y, which implies in place of x we have y plus a whole square, and e power minus lambda, in place of x minus a we have y square d of y. Now this time we will be having three integrals, but again don't worry, everything will be solvable only by using that Gaussian integral. So expectation value of x square equals root of lambda divided by pi, and let's put a bracket here. First integral would be minus infinity to plus infinity y square e power minus lambda y square dy, because this y plus a whole square would be y square plus a square plus twice ya, and plus minus infinity to plus infinity a square e power minus lambda y square dy plus, and there would be a third integral that would be ay e power minus lambda y square dy. Again, this one is the odd integral, so it would be 0. So there remains only this and this one. Let's put it like this, lambda divided by pi, and see here is the y square. Let me write again the Gaussian integral, integral y to the power, in terms of, let me write it in terms of x, okay, x to the power 2n e to the power minus alpha x square d of x equals 2n minus 1 double factorial divided by 2 alpha to the power n root of pi by alpha. Okay, so in place of n we have 1, so in place of n we have 1, so it would be integral y power 2 y power 2 y power 2 e power minus alpha y square dy. So it's like 2 into 1 minus 1 double factorial divided by 2, in place of alpha we have lambda to the power, in place of n we have 1 root of pi by lambda. So it's like 1 double factorial, which is again 1 divided by 2 lambda root of pi by lambda. Is that okay? So let's put directly here 1 over 2 lambda root of pi by lambda. This is the first one, plus a square, and this one we already know it's root of pi by lambda because we already used it twice above. So let's close it. Now let's multiply this whole thing, 1 divided by 2 lambda and root of pi by lambda, this is this thing, and let's multiply this factor, root of lambda divided by pi plus a square root of pi by lambda into root of lambda divided by pi. These two will go, these two will go, there remains only 1 over 2 lambda plus a square. This is the expectation value of x square, and probably we got the same result by using that method. Let me check this 1 over 2 lambda plus a square. Now let's do the another part, which is the standard deviation. We know variance is equal to the expectation value of x square minus expectation value x whole square. So we know this 1 over 2 lambda plus a square minus expectation value of x is a and its square. This will go with this 1 over 2 lambda sigma square. So this is the variance. So sigma is equal to 1 over root of 2 lambda. This is exactly we got by using that method, and since we use the same definition there, so there is no problem. Now let's do the final part of this question, which is plot of probability density versus x. Okay, rho of x is given as a e power minus lambda x minus a whole square. So obviously this is the Gaussian integral, and it is centered at x equals a. If it has been like this, a e power minus lambda x square, so this one is centered at origin, like here, so it would be like this. Okay, but since it is x minus a, so its peak is at x equals a. Let me write it a bit clean. Okay, so here is x equals 0, here is x equals a, so it's centered at this a, and let's say this is the peak value, so it will go like this, uh, a bit more clean, because it is symmetric about a, so it will be like this. And what is the value of at x equals a? If we put here x equals a, so it would be 0, e to the power 0 is 1, so it's a, so it is a, and we already evaluated a, that is the normalization constant, which is root of lambda divided by pi, so it is root of lambda divided by pi. So this is its plot. And thank you so much for watching, and stay connected with me.